Hello. In this video, we're going to go over some problems from the 2022 AMC 10A. This first problem asks for the value of this compound fraction. So let's simplify it starting from the innermost part and we'll work our way outwards. 3 plus 1/3 is this part at the very bottom, and that's equal to 9/3 plus 1/3. And so it's 10/3. So 1 over this quantity means to take the reciprocal of this fraction. So 1 over that previous quantity is going to be equal to 3/10. That's this. So now let's do 3 plus that. 3 plus all of that is going to be 3 plus 3/10, which is equal to 30/10 plus 3/10. And that is 33/10. And again, this quantity is inside a reciprocal, and so 1 over all of that is equal to 10 over 33. Then the last thing we have to do is add 3 to it to get our final answer. So 3 plus 10 over 33 is going to be 99 over 33 plus 10 over 33, which is 109 over 33. And that looks like it's option D. Now we have question 2. Mike cycled 15 laps in 57 minutes. Assume he cycled at a constant speed throughout. Approximately how many laps did he complete in the first 27 minutes? Well, if he cycles at a constant speed throughout, that means that if you take a fraction of the time, the amount of distance he covers will be that same fraction of the total distance. So if he does 15 laps in 57 minutes, and he does X laps in 27 minutes, then we can set up a proportion 15 to X should be equal to 57 to 27. You can cross multiply, so 57X is equal to 15 times 27. So the exact value of X is equal to 15 times 27 divided by 57. Now we only need to say approximately how many laps he completed. So can we change this to be a little bit easier to simplify? Because the answers are all 2 apart, that means it doesn't need to be that good of an estimation. So I think we can safely approximate this to be 15 times 27 over 60. And that's a good choice of approximation because the 15 cancels with the 60 and this becomes 27 over 4, which is easier to compute. That is equal to, it's 1 less than 28, which is 7 times 4. So this will be 6.75. What I did there was I increased the denominator, so this result should be a little bit smaller than the correct answer, and 6.75 is a little smaller than 7. So I think it's fair to say that the correct answer is closer to 7 than any of the other options in this list. Now we have problem 3. The sum of 3 numbers is 96. The first number is 6 times the third number, and the third number is 40 less than the second number. What is the absolute value of the difference between the first and second numbers? So let's call those numbers a, b, and c and turn all these words into equations. First we have that the sum of the 3 numbers is 96. The first number, which is a, is equal to 6 times the third number, which is c. And the third number, which is c, is equal to 40 less than the second number, which is b. And our goal is to find the absolute value or the difference between a and b. Now, We're given three unknowns and three equations, so it should be pretty easy to solve. But now the question is, what's the easiest way to solve this? In this case, I think C might be the easiest variable to solve for. I say that because uh, we have two equations where we can easily substitute in A and B based on what C is. If we rewrite this as B is equal to C plus 4D, then A and B can both be written in terms of C, and so I'll plug that into this top equation. We get 6C plus C plus 40, which is B, and then this is plus C. So this is A, this is B, and this is C. A plus B plus C is equal to 96. If I combine like terms, this becomes 8C plus 40 is equal to 96. Rearranging that, we get 8C is equal to 56. So C is equal to 7. And then you might think, why do we solve for C? We're looking for A and B. Well, we have A and B very nicely expressed in terms of C. It's very easy to find that A is equal to 6 times 7, which is 42, and B is equal to 7 plus 40, which is 47, and their absolute difference is 5. So this value should be equal to 5, and 5 is our final answer for this problem. And you could solve this other ways. Instead of solving for C, you could just try canceling C out of these two equations in two different ways and then finding A and B. That would also work totally fine. Now we're on problem 4, and it looks like another word problem. It's sort of word problem heavy at the beginning of the test. In some countries, automobile fuel efficiency is measured in liters per 100 kilometers, while other countries use miles per gallon. Suppose that 1 kilometer equals m miles and 1 gallon equals L liters. Which of the following is the fuel efficiency in liters per 100 kilometers for a car that gets X miles per gallon? So this looks like a standard unit conversion sort of thing. We are told that 1 kilometer is equal to m miles, and 1 gallon is equal to L liters. I'll write it like that, capital L for liters. Okay, and now we are told that we have a car that goes X miles for every 1 gallon. And our goal is to convert this into liters per 100 kilometers. That's interesting. It looks like the volume is on top and the distance is on bottom. So what I'll do is I'll find the reciprocal of this. I'll find kilometers per liters, and then I'll worry about messing with the details. So first, let's convert the miles to kilometers. We can do that by multiplying by 1 kilometer over m miles. Since 1 kilometer and m miles are equal to each other, multiplying by this is the same thing as multiplying by 1, but it allows these miles units to cancel out, so instead we have stuff in terms of kilometers. I'll do something similar for gallons and liters. I'll multiply by 1 gallon over L liters, and the gallons cancel out. And so now we're left with kilometers per liter. The numerator is x times 1 times 1, which is just x, and the units are kilometers. And the denominator is 1 times m times L, so it's going to be ml liters. Now, it's not asking for kilometers per liter, it's liters per 100 kilometers. So first let's introduce that factor of 100. So we need to multiply the numerator and denominator by 100. So that way the value doesn't change. It becomes 100x kilometers per 100 ml liters. So how many liters does it take to go 100 kilometers? Let's turn 100 kilometers into its own units, which I'll call U for units. Then we have 100 kilometers is equal to 1 units. Then the 100 kilometers combine, so it becomes x units per 100 ml liters. So we want liters per units, not units per liter. So let's just take a reciprocal of this. That's saying that for every 100 ml liters, we're going x units, and units just represents 100 kilometers. So this fraction, 100 ml over x, is what we're looking for. Where is that? Here it is. E, 100 lm over x, because the order that m and l in doesn't matter. Multiplication is in any order, so E is equivalent to what we're looking for. Okay, for problem 5, we have our first geometry problem of the test. A square ABCD has side length 1. Let's just start by drawing that. Something like that. Not a very good drawing, but I'll make it neater if I have to. A square ABCD has side length 1. Points P, Q, R, and S line each side of ABCD such that APQCRS is an equilateral convex hexagon with side length S. Oof. Okay, APQCRS. How do we do that? We got to put 4 more points on each of the sides. And we want A from P to Q to C to R to S. Okay, so A, we're going to go to P on this side, then Q on this side, then C on this side, then R on this side, then S on this side. And you can see that shape is hexagon-y, but we want to make it an equilateral convex hexagon. So I'm going to try and put P, Q, and R and S on these sides so that this shape looks roughly equilateral. Where is that? Maybe roughly here is where P needs to go. And then like Q goes here-ish. And roughly this is R and this is S. That way, if I make APQCRS, we're looking at this hexagon right here. That's a 6-sided shape, and it looks like all the sides are the same. What is the side length? We know the side length of the whole thing is 1, and we know that this side length is S. So this is S, and because this is the same side of the hexagon, or another side of the hexagon has the same length, so it's also S. We know the whole side length AD, the side of the square, so it's equal to 1. And we know AP is S, so PD should be 1 minus S. Similarly, we know that CD is a entire length of 1, and CQ is equal to S because it's a side length of the hexagon. So DQ is 1 minus S. And now we have a tiny little equilateral triangle, or no, not equilateral, right triangle up here with side lengths 1 minus S, 1 minus S, and S. If you're familiar with your special right triangles, you should know that in a right triangle where two side lengths are the same, a right triangle like this, if this is side length S, this is side length S, from Pythagorean theorem, this is x times the square root of 2. Applying that to this situation, here x is 1 minus S. And if we multiply by root 2, we should get the hypotenuse. So 1 minus S times square root of 2 should give us the hypotenuse, which is S. And of course, if you didn't know the special triangle, you can just use Pythagorean theorem. It gives you the exact same results. So in this case, we'll distribute the root 2. Root 2 minus S times root 2 is equal to S. So root 2 is equal to S plus S root 2. Which is equal to, if I factor out the S, it becomes S times 1 plus root 2. And then S is going to be equal to, if I divide this over, root 2 over 1 plus root 2. With these radical expressions, there can sometimes be multiple ways of writing them. Let's see if this answer is up there. It doesn't look like it, so you might need to simplify this somewhat. Okay, so how do we simplify it? Let's multiply by the conjugate of the denominator. So we're going to multiply this by 1 minus root 2 over 1 minus root 2. That usually takes care of the job if there's a root in the denominator. So we're going to get in the numerator, distributing the root 2 to the two terms, root 2 minus 2. In the denominator, it's difference of squares, so it's going to be the first term squared minus second term squared. That's going to be 1 minus 2. Yes, 1 minus 2. And that's equal to root 2 minus 2 over negative 1. And that's the same thing as just writing 2 minus root 2 because negative gets distributed to each of those. So 2 minus root 2 should be the answer. And that is choice C. So that should be the answer. We're on problem 6 now, which expression is equal to this large expression, the absolute value of a minus 2 minus the square root of a minus 1 squared, for a is less than 0. Okay, so this is all about absolute value. We gotta simplify this expression, keeping in mind that a is less than 0. So let's write it out. It looks like this. Now, you might be very tempted in saying that this quantity is just equal to a minus 1. Right? Because you might say, look, we're taking this a minus 1 expression, then we're squaring it, then we're taking the square root. Those are opposites, and so we're just going to get the result a minus 1. The problem is, you might not know this, squaring and square roots aren't exact opposites. They're close to opposites, but the difference is that you could square a negative number and a positive number. So negative 3 squared versus 3 squared, those both equal to 9, and that's allowed. But if you take the square root of 9, you won't get two results as the answer. The rule is that if there's two results, you always take the positive one. So the square root of 9 is 3. So there's asymmetry here between squaring and square roots. And so it's not correct to say that this necessarily equals a minus 1. What is correct is saying that this is equal to the absolute value of a minus 1. Because if it turns out this thing in the inside's negative, then we're going to get the positive version of it when we take the square roots. And if it's positive, it remains unchanged. And that's exactly what absolute value does. It keeps positive values unchanged and changes negatives to the positive version. So the square root of something squared is its absolute value. If you didn't know that, now you do. So now that we know that, what is the absolute value of a minus 1 if a is less than 0? Well, if a is less than 0, then it's negative. Subtracting 1 keeps it negative. So we're taking the absolute value of a negative number here. So if you're taking the absolute value of a negative number, you need to make it positive by multiplying it by negative 1. So taking the negative of a minus 1 gives us 1 minus a. That's what this turns into. So in this expression we're trying to simplify, I will replace, well, I'll do absolute value of a minus 2 minus, and this whole thing is 1 minus a. Right there. Now let's rearrange that. I'll distribute the negative sign. So it becomes minus 1 plus a. And that's the same thing as combine the a's, we get 2a. Combine the minus 2 minus 1, we get minus 3. And what is that? 2a minus 3? Well, we know a is negative, so multiplying by 2 keeps it negative. And subtracting 3 keeps it negative. So this whole thing is negative. Again, we're taking absolute value, so we have to multiply the whole thing by negative 1 to make it positive. It becomes 3 minus 2a. So let's see if 3 minus 2a is one of our options. It looks like it's the first option. So a, 3 minus 2a, should be the final answer to this problem. Now we're on problem 7. The least common multiple of a positive integer n and 18 is 180. And the greatest common divisor of n and 45 is 15. What is the sum of the digits of n? Okay, so we're taking the LCM of n and 18, and we're getting 180. And we're taking the GCD of n and 45, and we're getting 15. And to solve this, you just need to know how LCM and GCD work. When you're taking the LCM of two numbers, what you need to do is look at their prime factorization. So just as a random example, let's say we're looking at 2 times 3 squared times 5 times 7, and we're taking the LCM of this number and 3 to the third times 7 squared. To take the LCM, we just think of all the prime numbers that are involved and figure out how small we can make each of the exponents such that all of these exponents that are given are smaller. So for example, this second number has no factor of 2, so we can just include as many 2's as we want and this one's satisfied. But this top number needs at least 1 2 to evenly divide the results. So there needs to be, you can imagine there's an imaginary exponent of 1 here. So we need to put a 1 to the power of 1 here in order to satisfy the first value. Then for the second prime number, which is 3, this first number requires the exponent to be at least 2, and the second number requires it to be at least 3. So to satisfy both the smallest number, we can make the exponent just 3. For 5 only exists in the first number, and the exponent is 1. So the second number doesn't care. The first number requires it to be 1. So that turns into a 1 to satisfy both of them. And for the 7, this top number requires an exponent of 1 at least, and this one requires an exponent of 2 at least. So satisfy it and make the exponent as small as possible and make that a 2. So the LCM of those two numbers at the top is the product of these values. We can also take the GCD, which is a slightly different process. It's similar though. And this time, instead of trying to find the smallest number that's at least with these exponents, we're trying to find the biggest number that is in common with both of the exponents. So we won't actually include a 2 in this one, because there is no 2 in this bottom one. What about 3? We will include 3 because 3 is in both of them. And how do we make this exponent as large as possible while staying smaller than both of these exponents? Well, we can make it 2, because 2 fits into this exponent. 2 is less than or equal to 2. And 2 fits into this exponent because 2 is less than or equal to 3. But you can't go any bigger than that, because if we try making this a 3, that's too big. 3 to the power of 3 does not go into 3 to the power of 2, so that won't work for the first number. So it's kind of the reverse process. We're trying to find factors that are shared. There's no factor of 5 in this bottom one, so we'll just skip the 5 and go straight to 7. And using a similar process, this is going to be 7 to the power of 1, because 1 is the biggest number that is less than or equal to both of these exponents. And that's how you find LCM and GCD. Now we're going to do the same process, sort of, over here. We don't know what the prime factorization of n is, but we know it's going to be like 2 to the power, I'm going to write n equals, it's 2 to the power of something, times 3 to the power of something, times 5 to the power of something, times 7 to the power of something. And there might be more, we're not sure yet, but n is that. We just need to figure out what the exponents are to figure out what n is. We also have 18 and 45, so let me write those. Let me do 18 first. 18 is going to be 2 to the power of 1 times 3 squared. And so when we say the LCM of n and 18 is 180, we need to figure out what the prime factorization of 180 is. It's just 18 times 10, so by introducing an extra factor of 10, which is 2 and 5, we can turn this 18 into a 180. So I'll add an extra 2 and I'll add an extra 5. And that is how we should turn this 18 into 180. So we started with this mystery number, this number. Taking the LCM gets us to this number. So how does this 1 change into a 2? What that means is 2 is the smallest number that's at least both of these exponents. Well, why isn't it 2 to the power of 1 instead? Because 1 is less than or equal to 1. It must be something about this top exponent that's turning this 1 into a 2. So this top exponent actually has to be equal to 2. There's no other option. Why? If it was less than 2, then this exponent would be smaller. And if it was bigger than 2, then this exponent would need to be bigger. So 2 is the only value that makes this one work. 3 squared is a little bit different. Because this 2 down here is already forcing this to be at least 2. So it's possible that just using this bottom number, we're able to turn this exponent into a 2. What we can say is this can't be that big. This can't be 3, because then this would need to be at least 3. It can't be bigger than that, but it could be smaller. It could be 1 or 2. It's okay for it to be 1 because this bottom number is turning the exponent into a 2. And then the 5, this 18 doesn't even have a 5, so this n is definitely contributing the 5. It needs to be 5 to the power of 1, because anything bigger would make this exponent bigger. And we could actually say that for all the other prime numbers, they're all 0. They're not even part of this expression, because if they were, then they would also be down here, but they aren't. So now the only question is what's the exponent on top of the 3? So hopefully this bottom equation about the GCD will give us that value. So let's prime factorize the last two numbers, which are 45 and 15. 45 has no factor of 2. It's 3 squared times 5 to the first. 15 is going to be 3 to the first times 5. and that's the GCD. So, as expected, there's no 2 here because the 45 is missing a 2, and there's no other prime numbers here because 45 doesn't have any other prime numbers. It's just going to be 3 and 5. It makes sense that there's 5 to the 1 here because 1 is the biggest number that's less than or equal to 1 and 1. So it's just the 3s that we need to focus on. If this was a 2, then the biggest number that's less than or equal to 2 and 2 is going to be 2, which doesn't match. But if you made this a 1, the biggest number that's less than or equal to 2 and 1 is 1, so that's the only option that works. And so by looking at that last equation, we got the final value, and now we know that n is 2 squared times 3 times 5, which is going to be 2 squared is 4, and 3 times 5 is 15. That's 60. And all we need to do is find the sum of the digits of 60, which is 6 plus 0, which is 6. So 6 is the final answer. We're on problem 8 now. A dataset consists of 6 not distinct positive integers 1, 7, 5, 2, 5, and x. The average, arithmetic mean, of the 6 numbers equals a value in the dataset. What is the sum of all positive values of x? Okay, so the arithmetic mean is going to be 1 plus 7 plus 5 plus 2 plus 5 plus x over 6. And let's just simplify that. That's going to be 5 plus 5 is 10. 7 plus 1 plus 2 is 10. So it's going to be 20 plus x over 6. And so if this is equal to a number in the data set, there are a few not necessarily distinct options. Let's just enumerate them all. It's possible that this quantity is just equal to 1 because 1's in the set. It could be equal to 7 because 7's in the set. It could be equal to 5 because 5's in the set. It could be equal to 2 because 2's in the set. And perhaps the most interesting one, this quantity could be equal to x, because x is also in the set. However, if it turns out that x is the same as one of the other options, then this is not a new case. We'll have to find out by doing some work and seeing. So let's just solve all these equations very quickly. Or, you know what? Instead of solving them all immediately, I'm just going to do a more general form. We have a bunch of equations in the form 20 plus x over 6 equals m, where m is the mean. So if I rearrange this, x is going to be equal to 6m minus 20 after doing some rearranging. So we're summing up all positive values of x. So for this to be positive, 6 times m has to be greater than 20. So for all the options where 6 times the mean is not greater than 20, we can just eliminate them. So 6 times 1 is 6, which is not greater than 20, so we can just eliminate this option. 6 times 2 is 12, which is not greater than 20, so we can eliminate this option. So that simplifies things a little bit. In this first option, if I use this bottom equation, x equals 6m minus 20, this becomes x equals 6 times 7 minus 20, which is equal to 22. So that's a valid answer. X here is going to be equal to 6 times 5 minus 20, which is 10, so that's a valid answer. Here's a little bit different. We'll get x is equal to 6x minus 20. So 5x is equal to 20 after doing some rearranging. And x turns out to be equal to 4 in this option. That's a valid and different answer from the other two. So we have 3 different values of x, and so they're all positive. We can add them up. The answer to this problem is 22 plus 10 plus 4, which is the same as 32 plus 4, which is 36. So 36 should be the final answer. Choice D looks like it's the answer. Now we're on problem 9. A rectangle is partitioned into 5 regions as shown. Each region is to be painted a solid color. red, orange, yellow, blue, or green, so that regions that touch are painted different colors, and colors can be used more than once. How many different colorings are possible? Let me just copy this diagram down. We have a total number of choices of 5 colors for each rectangle. It doesn't matter what color we paint this first rectangle, we can do everything else in terms of it. So we can ask how many options are there for this first rectangle, and there are 5 because there are 5 colors to choose from when we color this rectangle in first. Then it makes sense to focus on rectangles that are restricted. So let's try coloring this rectangle second. Regardless of what color we choose for the first one, because these are touching, this rectangle will have 4 color options afterwards, whatever 4 are remaining. Now we can focus on coloring this one because no matter how these two rectangles are colored, this will have 3 options because these two are going to have different colors. So out of the 5 options for this rectangle, only 3 are remaining. Then we can ask about this rectangle next. Again, it has 3 options because of the 2 rectangles that we've colored so far, they're both definitely different and they're both touching this rectangle. So there's 3 color options left for this guy. And then for this guy, there's also going to be 3 options left because it's touching 2 rectangles that have already been colored and they're both definitely different because they're touching. So there's definitely 3 options left. So if you specifically color in that order, you can easily make a choice for how many options you have for each rectangle. And so the total number of options is going to be the product of all these numbers. 5 times 4 times 3 times 3 times 3. So 5 times 4 is 20. 3 times 3 times 3 is 3 cubed, which is 27. To easily multiply 20 times 27, first I'll multiply the 27 by 2 to get 54. And there's still an extra 10 left that I need to multiply by. So that turns into 540. So there should be 540 ways of coloring this diagram. And that looks like choice D. Now we're on problem 10. Daniel finds a rectangular index card and measures its diagonal to be 8 centimeters. Daniel then cuts out equal squares of side 1 centimeter at 2 opposite corners of the index card and measures the distance between the 2 closest vertices of these squares to be 4√2 centimeters, as shown below. What is the area of the original index card? And we're given a pretty funky diagram, but it shows what's going on. We have these corners cut out of this rectangle, and we have a different diagonal length as a result of that. And so, let's see what we can do here. I'm going to slightly redraw this. Let's start with making a rectangle. And then I'm going to draw the 2 squares, like that. Try to be a little bit neater. And we're given this length, which appears to be the diagonal of a smaller rectangle. I'll try drawing that smaller rectangle in now. Okay, so now I'll start labeling. This is 4√2. And the whole diagonal is 8, but I'll just keep that in mind. And these are side lengths of 1, which I think is important. So we're trying to find the area of this original index card. So that means to me that we should try finding its length and width. I'll call the length L and the width W. And since this is the diagonal of a smaller rectangle, I'm going to call this length L prime and this vertical length W prime. Actually, I don't even need to do that, I think, because it's pretty easy to write these in terms of L and W. Notice that the length of this rectangle is just 2 less than the length of this outer rectangle, because this horizontal distance is 1 unit, because it's parallel to this side length, and so is this is also 1 unit. So the length just becomes 2 units shorter than the original length of the index card. So L minus 2 is the length of this rectangle. And similarly, we have a vertical distance of 1 unit and a vertical distance of 1 unit here. And so W minus 2 is the length, or the width rather, of the smaller, I'll write it like this. W minus 2 is the width of the smaller rectangle. And of course, we have a right triangle here because this is a rectangle, which is great. But also importantly, oh, sorry, zoom out. If we look at the original rectangle, this is not a great diagram, sorry. We have W, we have L, and we know the diagonal is 8. So this is going to be length 8, and this is also a right triangle. So we actually have 2 right triangles, and there's 2 variables, L and W. So by using Pythagorean theorem twice, that might be enough to help us solve for L or W, or maybe the product L times W, because we're looking for the area, and the area is L times W. Keep that in mind. So I don't know yet whether we're solving for L and W individually or this product specifically, but let's set up some Pythagorean theorem equations. From this smaller right triangle, we have, I want to zoom in a little bit. We have L minus 2 squared plus W minus 2 squared is equal to the square of this length. And the square of 4 root 2 is going to be 16 times 2, which is 32. And from this other right triangle, we've got L squared plus W squared equals 8 squared. So L squared plus W squared is equal to 8 squared, which is 64. Okay, let's see if we can simplify this left-hand side by distributing out the squared factor. The L minus 2 quantity squared is going to be L squared minus 4L plus 4 when you distribute it all out. And similarly, this other expression is going to be W squared minus 4W plus 4. That's equal to 32. So I'm noticing we have L squared plus W squared, and we know it's equal to 64. So that looks like we might make a substitution in 1 second, but let me rearrange stuff. We'll put the L squared plus W squared together. I'll put the minus 4L minus 4W together. And I'll combine the two 4's, these two 4's, I'll combine them to create plus 8. And that's equal to 32. And looking at this, I'm just going to move the 8 to the other side. So this becomes 32 minus 8, which is 24. And now I'm going to use this expression and substitute L squared plus W squared for 64 right here. So it becomes 64 minus 4L minus 4W equals 24. And I immediately want to divide everything by 4. Everything here is divisible by 4. So we get 16 minus L minus W is equal to 6. And if I rearrange by moving the minus L and minus W to the other side, then moving the 6 over to this side, I'll get that 10 is equal to L plus W. Now, that is not exactly what I wanted. I wanted L times W, but I think we're actually okay. If you've never seen this trick, this might be a little tough, but we can create an expression that involves L plus W and these square terms and the product L times W pretty easily. All we need to do is consider the quantity L plus W squared. And why would we do that? Because if you distribute this, what do you get? You get L squared plus 2LW plus W squared. Notice that if you look at all the expressions here, we have L plus W, which we already know is equal to 10. We have L squared plus W squared, which we already figured out earlier is equal to 64. And the only thing that's left is LW, which is the area of the index card. That's what we were looking for. So we actually know everything here except for what we need, which is exactly what we need to solve for something. So L plus W is 10. I'll substitute 10 into here. L squared plus W squared is equal to 64. Let me just double check that. Yes. So L squared plus W squared I'll replace with 64. And then all that's left is 2LW. 10 squared is equal to 100, and if you subtract 64, you'll get 36. So 36 is going to be equal to 2LW, or in other words, LW, the area of the index card, is equal to 18. So it looks like 18 is the final answer to this problem, and it looks like that's choice E. So 18 it is. Here we are at question 11. Head mistakenly wrote 2 to the power of m times the square root of 1 over 4096 as 2 times the mth root of 1 over 4096. What is the sum of all real numbers m for which these two expressions have the same value? Okay, let's write this in a way that's less painful. First of all, it might be worth noting that 4096 is 2 to the 12th. How do I know that? Well, I just have the powers of 2 memorized to a certain point. So I already know that 2 to the 10th is 1024, which means that 2 to the 11th is 2048, and 2 to the 12th is 4096. As a math competitor, it's good to just know these quickly so you can easily recall them. So that seems like a good way to substitute these in. Let's see, how should I write this? We know we want values of m that make these quantities equal, so let's write inequality. 2 to the power of m times the square root of 1 over 4096 is equal to 2 times the mth roots of 1 over 4096. Okay, so let's first of all, mixing exponents and square roots seems kind of silly. So let's turn these square roots into, or mth roots in this case, into exponents. So this becomes 2 to the power of m times 1 over 4096 to the power of 1/2, because that's the same thing as taking a square roots. And that's equal to 2 times, and here we have 1 over 4096 to the 1 over m, because that's what taking the mth root means. And now I'm going to use the fact that 4096 is 2 to the power of 12 and rewrite these. This is 2 to the power of m times 1 over 2 to the power of 12 to the 1/2 equals 2 times 1 over 2 to the 12th times 1 over m. And 1 over 2 to the power of 12 is actually the same thing as 2 to the negative 12. Right, that's right. So this is equal to 2 times m to the power of m times 2 to the negative 12 to the 1/2. And this is 2 times 2 to the negative 12 times 1 over m, or 2 to the 1 over m. Now we can use exponent rules. We can multiply these exponents together to simplify them. So it becomes 2 to the power of m times 2 to the power of negative 12 times 1/2 is negative 6. And this is going to be 2 times 2 to the power of, I'm going to put the times symbol there, 2 times 2 to the power of negative 12 over m is this one. And when you multiply exponents with the same base, you just add the exponents together, so this becomes 2 to the power of m minus 6 is equal to 2 to the power of, there's an imaginary 1 here, so it's 1 minus 12 over m. And this is only possible when the exponents are the same, so this is equivalent to saying that m minus 6 is equal to 1 minus 12 over m, which is a lot simpler of an equation to work with. And I don't think we even need anything that we just figured out. So I might just take all this information and drag it up, or copy it up, to stay closer to the problem. Now let's multiply everything here by m, because I want to get the m out of the denominator there. So it becomes m squared minus 6m is equal to m minus 12, and let's just rearrange that. Let's move this m minus 12 step over. Let's turn this into a proper quadratic equation. M squared minus 7m plus 12 equals 0. And that's easy to factor. We need two numbers that multiply to 12 and add to negative 7. That seems like negative 3, negative 4, so m minus 3 times m minus 4 is equal to 0. So m can be either 3 or 4. And those seem right because there's nothing wrong with taking the third root or the fourth root of an expression And I don't think anywhere else is there a problem with those particular values. So I think m equals 3 and 4 both work, so those are the only solutions. And the sum of 3 and 4 is 7, so it's asking for 7 as the final answer, choice C. Okay, the final problem I'll be covering today is problem 12. Let's see what it is. On Halloween, 31 children walked into the principal's office asking for candy. They can be classified into 3 types. Some always lie, some always tell the truth, and some alternately lie and tell the truth. The alternators arbitrarily choose their first response, either a lie or the truth, but each subsequent statement has the opposite truth value from its predecessor. The principal asked everyone the same 3 questions in this order. Are you a truth teller? The principal gave a piece of candy to each of the 22 children who answered yes. Are you an alternator? The principal gave a piece of candy to each of the 15 children who answered yes. Are you a liar? The principal gave a piece of candy to each of the 9 children who answered yes. How many pieces of candy in all did the principal give to the children who always tell the truth? Wow, okay. What a complicated issue. So let's think about how to approach this systematically. This problem says they can be classified into 3 types, but I actually think it might make more sense to classify these children into 4 types. There are the children who tell the truth, the children who always lie, the alternators who start by saying yes, and the alternators who start by saying no. Let's think about what answer each of these groups of children would say to each of these questions. Uh, let me label the 3 questions. 1, 2, and 3, okay? The first question is, are you a truth teller? Well, the truth teller is going to say yes, and the liar is also going to say yes because they lie. They're not a truth teller, but they lie about it and say yes. The alternators, ooh, I put the wrong letters here. Oopsies. They're the alternators who start by telling the truth and the alternators who start by lying. That's what I meant to put there, my bad. So, for an alternator who tells the truth at the beginning, well, when told they're a truth teller, they're not, so they're going to honestly say no. But if the alternator starts by lying, they're going to actually say yes, to lie. Now the second question, are you an alternator? Well, the truth-telling person's going to admit that they aren't, but the liar is going to say that they are, because they want to lie. The alternator, who started by telling the truth, is now going to lie about it. So, are you an alternator? They're going to lie and say that they're not an alternator. On the other hand, the alternators who started by lying are now telling the truth, so they will truthfully say that they are alternators. And the final question is, are you a liar? Well, the truth-telling person is going to admit that they aren't a liar. The liars aren't going to say that they're liars because they're lying, so they're going to falsely say that they aren't liars. The alternators who are telling the truth have now alternated back, so they'll keep saying the truth now, and they'll admit that they are not liars. On the other hand, the alternators that start by lying, well, they're still lying, so they're going to say that yes, they are liars. They're not, they're alternators. So it looks like the alternators who told the truth at the beginning never got any candy, and alternators who lied always got candy. That seems a little bit unfair, but that's not what we're being asked. We're being asked how many children are there in each of these groups, I guess is what we're being asked. We know there's 31 children total. Okay, so how do I keep this in mind? Let's say that there are A, truth tellers, B, liars, C, alternators who start by telling the truth, and D, alternators who start by lying. So if there's 31 children total, then we know that A plus B plus C plus D is equal to 31. Now, I'm going to start with this final statement, because the principal gave a piece of candy to the 9 children who answered yes to his last question, but only this final group answered yes. So if the principal gave 9 pieces of candy, that means that D is actually equal to 9. Okay, now I want to work on the second to last question. The second to last question The principal gave 15 pieces of candy to the second and fourth groups. We know there are 9 people in the fourth group, so there must be 6 in the second group, to a total of 15. The final thing is the principal gave a piece of candy to 22 children who said yes to the first question. That includes the 15 people from before, actually, plus 7 more for the truth tellers. So A is equal to 7. And I don't think we actually need to figure out C at all for this question, but in case you were curious, it looks like from this equation and these 3 values, I think you can solve and get C is equal to 9. I don't think it's necessary. We just need how many pieces of candy did the principal give to the children who always tell the truth. Well, the children who tell the truth said yes 1 time, and there's 7 of them, so they received 7 pieces of candy. A is the answer. And that's it for this test for now. I might upload another video in the future covering the rest of the test, but keep in mind the questions do get harder, so we'll have to do some harder questions if I continue this video series. Well, hope to see you next time.